Okay, Assalamualaikum warahmatullahi wabarakatuh and greetings to all. Today I would like to present our group project Mechanism of Materials, and we are from group 6. So this is our members. We have Daria, Ryan, Haris and Afifa. So the introduction of this project is the purpose of this project is to investigate the bending behavior of structural member made from uncooked spaghetti. Through this project, we are able to apply the concept of shear force, bending moment, stress analysis and safety factor that we have learned in Mechanism of Material class. So the experimental result will also help us to understand how structural member behave under bending loads and how failure occurs in real real engineering application. So we have 5 objectives for this project. The first one is to fabricate a circular spaghetti beam using uncooked spaghetti. The second one is to study the effect of gradually increasing loads on the beam. And after that, we want to determine the failure load and the corresponding bending stress of the beam. Number 4 is to generate the shear force diagram and bending moment diagram for the applied loads. And the last one is to calculate the allowable normal stress using safety factor of 1.5.
So for the model fabrication method, in this project, we design and fabricate an equilateral triangle cross-sectional beam with a length of 30 cm and a thickness of 1.5 cm according to the project requirement. Firstly, we arrange a few spaghetti side by side parallelly and combine it with oil glue until they reach the diameter needed. Make 3 pairs of wall and combine them of every end to become 3 equilateral edges. Next, wrap the empty triangle with paper to become the mold. Then fill in the triangle with spaghetti and put in the oil glue and ends all the edge with hot glue. Then let the glue dry. After that, we can take out the model and the model is ready to be tested.
Assalamualaikum warahmatullahi wabarakatuh. My name is Daria Abdullah. We are from group 6. Today we want to test our equilateral beam, triangle beam. So let's start.
First, try with one bottle. Okay, okay. Ini gila. Ini mana? Nah.
So hello everyone. So for the next part of the slide, we will go through the calculation. So I will take you through the structural calculation of a simply supported beam subjected to a point load as shown on the left side of the slide. So we begin with a beam of a total length of 0.30 meters with a point load applied exactly at the midpoint. So point B, which is 0.15 meters from both ends. First, we calculate the weight of the load given a mass of 1.5 kg and using the gravitational acceleration, which is 9.81 meter per second square, we get a downward force of 14.715 Newton at the center. So now we apply the equation of static equilibrium to find our reaction force of AY and CY. So by summing the forces in the vertical direction of summation of Fy equals to 0, we know that Ay plus Cy equals to 14.715 Newton. So to solve for these individual reactions, we take the sum of moments about point A, which is the summation of moment A equals to 0, which gives us the equation of negative 14.715 in bracket 0.15 plus Cy in bracket 0.30 equals to 0. So solving for Cy, we find it equals to 7.356 newtons. So substituting this back into our vertical force equilibrium, Ay is determined to be 7.358 newton because the load is perfectly centered, so the forces are symmetrical. So now we're moving on to the section analysis. So now we choose the interval from 0 to 0.15. So we sum the vertical forces, which is 7.358 minus V1 equals to 0, which gives us a constant internal shear of 7.358 Newton. So for the bending moment, we sum the forces at the cut of a summation of m equals to 0, which is negative 7.358 x plus m equals to 0, which leads to a linear equation of m equals to 7.358 x. So at the start of the beam, which is x equals to 0, the moment is 0 Newton per meter. And then at the midpoint, which is x equals to 0.15, the moment reaches 1.1037 Newton meter. So moving on to the interval of 0.15 to 0.30. So the vertical forces equation becomes 7.358 minus 14.715 minus V1 equals to 0, which drops our internal shear force to a negative value, which is V1 equals to negative 7.358 Newton. So setting up the moment equation at the cut, we get negative 7.358 x plus 7.715 in brackets x minus 0.15 plus m equals to 0. So simplifying this gives us the moment equation of m equals to negative 14.715 in bracket x minus 0.5 plus 7.35x. So we test our boundaries at the midpoint, which is x equals to 0.15. The moment we get is 1.1037 Newton meter, and it tapers back down to 0 Newton meter at the far right support, which is x equals to 0.30. So as we can see the shear force and bending moment diagrams, we see that as we plotted in the top graph, which is the shear force, the shear force starts at a positive 7.358 Newton for the first 0.15 meter. Then the moment it hits the central point load, it drops by 14.1715 Newton, staying a constant at negative 7.358 Newton for the remaining half of the beam. Now we move on to the bending moment diagram, which is the bottom graph, which shows a linear distribution for a point load. So the moment builds up linearly from 0 at point A, peaks exactly under the load at 1.1037 Newton meter, and then it symmetrically decreases back to 0 at support C. So this is all the calculation that we have calculated.
The last part of conclusions and summary. This project successfully transformed theoretical engineering concepts into a practical design through detailed calculation and systematic analysis. The calculated results show that the proposed design is capable of achieving the desired performance within the specified operating conditions. The obtained results indicate that the proposed design is feasible, efficient, and capable of fulfilling the required operating conditions. Throughout this project, we gain valuable experience in applying engineering equations, evaluating design assumptions, and interpreting calculation results. Although this represents a preliminary design, it provides a strong foundation for future optimization and practical implementation. This project has also improved our understanding of the design process, calculation methods, and the importance of making reasonable engineering assumptions. Thank you.